So, hello everyone. Sorry, we had some technical issues. Today, we have a very special guest speaker, Professor Lei Zuo. Professor Lei Zuo is a professor at Virginia Tech in the Department of Mechanical Engineering. He earned his bachelor's degree from the University of Tsinghua in China in automotive engineering. And then he earned 2 master's degrees in electrical engineering and a PhD in mechanical engineering from MIT. He's also the director of Center for Energy Harvesting. And his research interests include robotics, autonomous and dynamical systems. Today he will talk to us about energy harvesting. So please join me in welcoming Professor Lei.
Thank you so much for the introduction. Okay. I'm Lei. I'm going to talk about energy harvesting and especially for transportation system. And before that, I want to mention that we have energy harvesting center at the Virginia Tech and campus. And this is Industry University Collaborative Research Center. That means we do something between industry, applied research, and university research. This center has been there for more than 10 years, and Columbia University just let me hide this so that people can see and hide. Okay. So Columbia University joined in 2017 and Penn State joined in 2019. This center is I didn't go next page. Okay. This center is governed by the industry members. Basically, the NSF gave us the operation budget. Then we get money from industry. So university reduce overhead. About my research, I work on energy harvesting from different scale and some. Okay, let me say that. Okay, and some energy harvesting like megawatt level, electric type of cell, and energy harvesting from ocean or wind from tens of megawatt level. Okay. And energy harvesting is really applied research. So the knowledge you use like vibration, dynamics, control, electronics, thermal fluid, and smart material in sensors. Okay, so today I'm going to talk about energy harvesting from vehicle, transportation, and ocean used for the transportation system. Okay. So first I talk about a small scale energy harvesting, usually milliwatts level, microwatts level. I give one example about smart tire energy harvesting. Then talk about energy harvesting from vehicle. We talk about 100 watts energy. Then talk about transportation infrastructure energy harvesting. Specifically, I mentioned the railway track energy harvesting and speed bump. Then talk about the ocean energy harvesting. Okay, then give my conclusion. So energy harvesting is a multi-billion dollars market. So that is so let me say that way in April. So that survey is based on one company's research. Okay, and you can say most of the company work on the vibration and the solar PV type of energy harvesting, and some company work on thermal heat energy harvesting. Okay, and this. Okay. Okay, so For thermal energy halving, it has been used very popular. You put a solar light on the road, right? The principle is here, okay. And with heat energy halving, you usually have temperature difference. Then you generate the voltage. And vibration motion is many the talk today. You use piezoelectric material or use electromagnetic material for energy halving. So that figure shows some very interesting application of different energy halving at its small scale. And for example, in automobile, you may have some tire pressure sensor. Most of tire pressure sensor is powered with battery, and you can have energy to power that too. This is solar to power small windows circulation when you park the car, right? So energy halving has been used for industry, and for example, you have such kind of water, and you can use vibration energy halving to power the sensor. This chemical plant, you can use thermoelectric energy halving to power sensor directly. And the building up vibration energy or motion energy halving, like in the building, if you have a light switch, you have to go through all the pipe to the wall, right? There's a company who commercializes this type of energy halving. There's piezoelectric cantilever inside. When you push the button, it halves energy. Then you can avoid such kind of wiring. Like same thing as you use remote control to control the TV. Now you can use that to control your light without wiring behind the wall. And it has been used for the defense type of application and civil structure. For example, this bridge, you can put energy hubs there for the sensors. And the emergency application like medical device and portable device use pacemaker, right? You have energy and power the pacemaker instead of you have every 5 or 10 years the patient needs to go through surgery to change the battery, right? There's a commercial watch. You can like this pendulum. When you swing your arm, it takes this generator charge energy, and you don't need to change the battery. So the different type of energy halving look like this tire pressure. This is 100 microwatts or less, right? Like watch is microwatts energy. Those are the micro milliwatts energy. So energy halving, the principle. Okay. Take a look at this two most popular type of electromagnetic and piezoelectric. So no matter what, there's vibration mass, right? And then there's vibration. And you can write the modeling this mechanical certain vibration and the voice coil or piezoelectric. It generates a voltage or generate a current through this piezoelectric electromagnetic transducer. Then you get energy out directly. This is modeling for the piezoelectric electromagnetic energy halving. And this essentially you use resonance. The condition is here. You need two conditions so that you can get an energy out. So first, you have frequency match. When you have the system work at the resonance, you have maximum vibration amplitude. You get more power output. Second is damping matching, right? So you need to design the power electronic circle so that when you charge the system, you introduce damping. The electric damping or energy halving damping should match the mechanical damping. In that way, you get maximum power output. So I mentioned about a small scale energy halving for tire, right? Nowadays, all the new car, you have to put a tire pressure monitoring sensor, okay? And the tire pressure monitoring sensor is 2 minutes, you take one data. Therefore, most of the battery lasts for years. Nowadays, for vehicle control side, you can say to implement the control, you usually need 200 hertz sampling, right? So 200 hertz, this is 0.5 data per minute, and this is 1,200 data per minute. Therefore, you use battery. The battery will not only last for days. What we can do, we can harvest energy. Another motivation is just think that way. Now people talk about intelligent vehicle. They put a camera there and put all kind of sense to sense the road condition. And but you don't have sensor here on the tire. What's look like? You are walking, you use the eye, you don't have sensors on your leg. Can you imagine, can you walk there? You not walk where, right? So there's a need to power the tire, get smart tire. However, smart tire is not very easy to power because the implication. So tire has been there, all this topic in the energy halving. Since energy halving started 15 or 20 years ago, people looked into tire, but it's very challenging. First thing is vibration, right? I mentioned that for vibration energy halving, you need to create a resonance. And in that way, you have large vibration. Now, the tire root roughness is more like a random vibration. Random vibration, you cannot create resonance, right? Another thing is you have large centrifugal force on the tire. You have up to 200 G. Another certain vibration after 200 G is sent in one side. It wouldn't vibrate that easily. And third is resonance. Now, suppose you find the best frequency. However, when you drive the car at different speed, and this excitation frequency change. So what we can do? So this is solution. Okay, we talk about stochastic resonance before we present our self-tuned stochastic resonance. Stochastic resonance. I would like to mention this background. So stochastic resonance, you need three conditions. One is bistable system. What's bistable system? You put a cantilever beam upper or vertical direction. You just imagine that way. Under gravity, this position is equilibrium but not stable. They will go this way or that way. This stable status. This is bistable. This one position stable, another position stable, right? And you need a bistable system. Second thing, you need a noise. And you use random excitation. And third is your wake period. If you meet these three conditions, the vibration at a certain frequency suddenly magnified. That means if you have random excitation, the amplitude is very, very small. And now you have random excitation and weak periodic excitation. The amplitude can increase 10 times, 50 times, like that. So this frequency, it will depend on the stiffness, first order and third order stiffness. And it will also depend on the excitation noise. If your noise reach certain level, as I said, you suddenly increase the frequency. The reason this is how it works. So normal situation, if you have random excitation, it only vibrate at this equilibrium position, very, very short, small range. Okay, because this random excitation and that changes the potential wear. Potential wear, just imagine that is display force time displacement is potential function. You do integration, okay. So because the integration term here, you have displacement and excitation come together, okay. Therefore, you have the noise will make this potential wear change. Like this, you can imagine that way, small vibration around this range. Because of noise, it makes this ball easily to fall to this side. And after where wake period, it can come back again. So that is how stochastic resonance works. When it meets the three conditions, bistable, random excitation, wake periodic, you suddenly magnify the motion, you get more power. Okay. So now come back to the tire situation. Tire, as I mentioned, you have weak periodic excitation. You have random excitation from ground, right? You have gravity when it roll over and gravity change. and gravity is just 1 g. Keep in mind you have eccentric force can be 200 g. This is called weight, right? And now we use eccentric force to create bistable system. And in this example, I say this is gravity. Makes sense. Backward, you have this stable status, this stable status. Now the gravity become eccentric force, right? You have 200 g. You put a beam here. Beam will not stay here. Will stay this side or another side, right? So now all the 3 beta sense, random excitation, right? And this is weak periodic excitation. This frequent. This depend on how quick you drive the car, and you have eccentric force. All 3 beta sense become 3 good sense. Okay. So we create a stochastic resonance. More important is self-tuned. What does self-tuning mean? Okay, this buckling and it will depend on the rotation speed, right? So you wouldn't be surprised that you can tune the stochastic resonance at a different rotation speed, a different tire, different vehicle driving speed. Okay, so we create this prototype, we mount there, and so this small video, let me show you the small video here. Okay. So this is vibration, and this is electromagnetic we put here. This. So after that, we mount to the tire and we draw the road. So then this is show you what happened, right? So we recorded the result. Or you can say, instead of only tire pressure sensor need 100 or 30 microwatts, we get 10 to 20 milliwatts in very, very large range. In that way, we can enable the smart tire. Okay. So this is small scale energy halving. When I come back to university in 2008, so in that time, a lot of people already work on the energy halving. So I think I want to work on a different large scale energy halving. So I mentioned the small scale energy halving is just a vibration problem, no matter linear, nonlinear, right? So large scale energy halving is unique. Like at the civil engineering, the tour building vibration, that is my first NS project. And another thing is vibration from the suspension system. So what's the unique is, let us say, okay, take a car as an example, right? You must have vibration source. You need to understand the road roughness, right? This excitation, right? You need to understand the vibration mechanics system. So this vibration frequency usually is low, 1 to 10 hertz. And you need a motion magnification or a transmission. Then you have transducer, piezoelectric, electromagnetic. Now we are talking about 100 watts energy. You need to how to integrate into energy storage device, right? More important for this car suspension like that, your priority is to not to harvest energy. Your priority is to reduce vibration, right? Energy halving is a secondary benefit. What I mean now, the unique challenge in summarize, okay. We first need to consider the vibration reduction. Then energy halving is secondary benefit. Second thing is not just a vibration system. We need to think about the transducer material, mechanic system, and design control electronics, right? And we need to take a system level approach, not just a vibration itself. So for myself, and I have all the background needed for this multidisciplinary research. I had my bachelor degree in vehicle, right? And I also have double E degree deal with electric circuit. I developed some circuit like that. Okay. And when I was in graduate school, I work on the vibration control. This is my master thesis work. This is my PhD thesis work. I worked in Chicago for 4 years in a pharmaceutical company. And in this pharmaceutical company, we developed a robotic system for the pharmaceutical R&D level automation. So I have the background of vibration control vehicle design. I think I can create a new area in 2008. Okay, that I can do better than any other people in the field who already work on that. So this is not just energy housing. So I apply this for the, as I mentioned, for the tour building, I did mention, and I also apply for this for the transportation system, like a vehicle. Okay. Nowadays, vehicle and transportation more and more interact together. It's not like a DOT only found the transportation, DOE look into vehicle, right? Now DOE also look into the infrastructure, and DOT also look into the vehicle. Okay. So how much energy is available, right? So we can, I do some modeling work, take the road roughness into consideration, vehicle dynamics into consideration. The conclusion is, on the good road, we can 100 watts from car, and on the average road, we go 400 watts. And the most important is the vehicle speed. You drive faster, you feel more bumpy, right? You have rough road, vibrate more. You pump air into the tires, skip, you have a bumpy, you feel more vibration. All these 3 parameters, they dominate how much energy you can harvest. So what 100, 400 watts mean? When you, this is BMW's data, okay. This is BMW Y530, and for this car, when you drive on the road, you take this new European driving cycle, you can remove all the unnecessary electronics. In such kind of case, it consumes 300 watts electricity. This electricity is provided by alternator that corresponding to 4% fuel. What I mean, if you have 1 to 400 watts energy, you can increase the fuel efficiency by 1 to 4%. So you consider we have 250 million vehicles, the total energy you can harvest is the energy saved per year is more like 10 billions, right? Depending on which kind of car, you have truck, bus, you drive a lot of time, you can get payback time in 1 to 2 years. Okay, so how to get energy out? So that is one design we implement. I call it mechanical motion rectifier. So this look like that rectilinear system, and there's some special set. Let me show you this video. So look at here, and to see what happened. You say this, it shows two motion, rect more up and more down. And your generator rotate one direction. So there's a one-way clutch in between. So in one direction, this one-way clutch engages this drive here. In another direction, this one-way clutch engage the drive the generator in the same direction. In that way, no matter your suspension move up and down, my generator always rotate one direction. So this is called a mechanical motion rectifier. So as you know, it's a vibration system. We generate a vibration type of signal with a positive voltage, negative voltage. Then you need a rectifier to change to DC. Then you store into the energy storage battery like that. Okay. Now we can, if we now the generator rotate one direction, you don't need the electrical components. You can generate DC. But now our advantage is not just rectify the voltage. Okay, that is in principle it's analog to the electrical voltage rectifier. Electric voltage rectifier, you have AC voltage, right? You can generate output most of cell phone, whatever computer you use DC. That's what's inside. You have AC to DC. AC to there are two important components we need to consider. Semiconductor diode allow current to go one direction. So previously it's AC, now it become like that, DC, right? There's a smoothing capacitor which makes the voltage stable. Now, in mechanical domain, we have one-way clutch. this allow motion go one direction. One way clutch you use probably every day when you bike the bicycle gear, right? And when you drive the car, your engine starter, the motor can drive the engine cannot drive the motor. There's a one clutch inside. Okay, so then the flywheel can stabilize the rotation. So the advantage is high efficiency. Previously, the generator in oscillation. Now, generator always unidirectional rotation, right? And another advantage, high reliability. And the reason is now generator rotates one direction. You don't need to worry about impact and backlash in the gear space, the gear engagement, disengagement, right? So you also get a better vibration control. And that means usually, let me say that way, as a control engineer, you can imagine that way, you have large mass, usually you cannot drive the system too quick. This inertia is a problem. Now inertia will help us. Inertia rotate one direction is act as the flywheel. So here, this is the road test result. We put this in the suspension here. We draw on the road. So you can say 2 to 4 millimeter vibration. We get 15 to 100 watts from one shock. So there are 4 shock over, right? As you expected, you drive a higher. This is a very low speed, 50 miles per hour. At a higher speed, you have higher power. You get more than 200 watts. Okay. So so another thing I mentioned for willful energy harvesting like that, our priority is not to harvest energy, right? You talk with the automotive engineer, this guy is always saying, okay, can you replace my car shock absorber? And yes, can you get better performance? The answer should be a yes. Let me show you why. And first say the experiment result first. This small truck, and we put our shock absorber there, we drive on the road. There are 3 different colors. The red line shows the result without the shock absorber. I just disconnect the shock absorber at all. Then the green line shows there's a shock absorber OEM existing oil type of shock absorber there. It is the energy dissipated, right? The blue line shows our energy of the shock absorber. We measure the acceleration here. You can see the acceleration with our own shock absorber and the vibration amplitude decreased. So what's the reason? So the reason is the vapor dynamic side. When you harvest energy, when you take energy out, it has damping effect, right? The damping. And another thing is, in this system, we have motor rotation. You have there's they call it inerter. Okay, what's inerter? Okay, that's a J damper. Inerter has been used in the F1 car race in the 1980s. Okay, this company treat us secret. They always have very good performance. Later, and F1, this guys realized that the band that you cannot use this your damper in the race competition. So inertia is like that. It generates force proportional to the relative acceleration. It's not F equal ma. You have a force proportional to the absolute acceleration. And it's like that when you drive the shock absorber, the flywheel or generator rotation inertia, right? When you have acceleration, the flywheel or generator will accelerate. So this is jet damper effect. And third thing is a nonlinear effect, because you have this linear rotation and 2 directions, you convert into 1 direction. Because this is called a linear jet damper with damping. Therefore, if we design this parameter where you can control the vibration of suspension better. So this is energy harvesting from suspension. In one conference I attend, this is CRRC, and I attend one one conference. During the conference break, I meet one person from CRC, China Railroad. Okay. And they said, okay, can you use that for the railway transportation? And he invited me to visit the company. His reason is, just imagine that way, the railroad, each segment, right? Usually freight train, there's no electricity. So people talk about intelligent smart transportation. Each part you don't have electricity, how it can be smart, right? So for them to send goods from one location to another location in the way we need to combine different segments of cars. So each year the north south such kind of cars because they don't know where it is. Half a year later, after they pay the person who send the goods after because they lost that, right? They don't know where it is. Half a year later, they find it out, but they already paid the compensation for the loss. Anyway, they want me to develop something for to track each car. So it's a freight train, and we did that. Okay, we put our shovel over here and have energy, and we test on the road, and we have 20 kilometer per hour test. We get 2 to 10 watts. Then enough power, a lot of sensors. Okay. I want to say that way, when he first approached me, I say, I already done a lot of work. Give me 1 year, I can give you working prototype. The real life is not like that. The car and the railway are different. So that is 20 times heavier than a car. Although the space is almost similar. Therefore, the design pretty challenging. Okay. So this energy halving from vehicle side, I want to talk about energy halving from transportation structure. And like a steel railroad, right? And another railroad in the tunnel or on the bridge in the remote area, it's really, really hard to power that, right? So on the track side, there are a lot of different devices, synchronized hot box, gate crossing, wireless communication, structure test monitoring, right? All of this need power, right? So now we want to provide a solution to power the railway track. Okay, it's not on the track, okay. So that is one solution we provided and test. That is on the crushed stone, the type of railroad, okay. And this vibration is pretty large. So you can see here, this is recorded test in PPCI, okay. And that is 5.7 millimeter deflection. We can get 7 to 60 watts energy. That is 30 times larger than the best research supported by US GOT. Okay, so this can power a lot of different sensors. Okay, so another thing is transit rail. Transit rail usually they set on the sleeper concrete. In this type of thing, the vibration is very, very small. Instead of here, this is 5.7 millimeters. So this is just a couple millimeters. So in this one, we have another design. Instead of mount our harvester on the tie, we mount our harvester on the track directly. And this is design, and also this is the test. So I will show you a video. Yes. So this is a little bit slow. This is a generator here. This mounted on the track. When the train passes by, the generator rotates. We have energy. This one we get about 2 to 10 watts of gain. And another work we did is speed bump energy harvester. Like one of the neighborhood, you have speed bump, Even in the highway, you have toll booths, right? You need to slow down the traffic. So we can harvest energy from the speed bump. So this prototype we developed. This is move up and down this brain, this generator inside. So this test, this speed bump here, and we just use wood track. We build that. Just drive the car. This light we can light up. So this is one phase we get 200 watts. Later we improve the design. We can get up to kilowatts energy from the speed bump. So the peak energy. So we also have energy from the filament. So it's like that you put on the road. When you step on that, you have energy. Okay, I have too many videos. Let me skip that one. So another thing, on-road energy harvesting, right? So you want to build a smart transportation. You just imagine the way you put a harvester on the road. I know Texas, California, and New Jersey State that support people to put piezoelectric on the payroll. Here we build a box, electromagnetic. So piezoelectric you get milliwatts energy, right? The peak. This experiment result, we drive the car 5 miles to this 2.5. Okay, 2.5 miles and 10 miles per hour. You drive that, we can get up to 20 watts energy from the energy harvester on the road. So, oh, this is the test. Okay, so you can say you step on that, you get energy harvesting. Okay, so we also get energy harvester on from shoes, right? You put inside or use inside like a insole. Okay, and you walk, you can get energy harvesting. Just imagine that way in the. If you have this type of thing for the roadside highway speed walker, right? You can harvest energy from the shoes. Then this shoes energy harvester can send data to the car. You can make the transportation system safer. So I want to briefly talk about marine energy harvesting, and so it's a little bit off topic, but still can be used for transportation system or for autonomous vehicle. This is just one example, right? Like fish farm, you can have energy to power the underwater robot to clean the fish farm. And that itself, it can be a robotic system too, like a boat, right? You can navigate this to the place with a high ocean wave. After you have energy, you can come back to the fish farm to power the system, right? We just get one project from NSF National Robotic Initiative. This ocean-powered robot for autonomous fish farm. And another idea is just more from marine energy to hydrogen. And so marine transportation, 70% of goods are transported by the ship. So it consumes a lot of energy. And one way people look into is electrify this type of ship. They're using hydrogen to power that, right? Hydrogen usually is used split the water into oxygen, hydrogen. Just imagine that way. Now you can build energy harvesting from ocean. You can produce hydrogen when the ship passes by. You can recharge the ship with hydrogen, right? So energy is challenging, but the energy is there in the ocean. So this is called blue energy, okay? And the blue energy comes from this map, okay? This is blue Earth, right? So blue energy, typically we say 3 types of energy, and ocean wave energy, tidal energy, ocean current energy. And broadly speaking, it also includes the river current and ocean thermal energy and offshore wind energy and marine biomass. So take ocean wave energy example. Okay, ocean wave energy, the total power density is very, very large. The power density compared with solar is 10 times larger. Okay, and the total potential along U.S. coastline, the wave energy is two-thirds of electricity generated from all resources. The first pattern was 200 years ago. But now, if we say ocean wave energy, you don't know what kind of ocean wave energy it is, right? It's not your fault, it's our fault because we didn't develop ocean wave energy converter so good yet. So far, there's no research convergence. It's pretty challenging. And there are several challenges. One is vibration. The wave is kind of vibration. Your frequency shift a little bit, the vibration can significantly reduce, right? It's sensitive. And another system is vibration, the frequency changing. And another thing is the amplitude, the wave velocity is still very, very slow, like 1 meter per second. If you need another power output, that means power equal force times velocity, you have huge force. So makes system pretty challenging. So that's a different type of wave energy converter in literature. And so far, no one knows which one is best. Even no one have the widely accepted criterion to judge which one is best. So I work on I come back to university in 2008. I mentioned I work on the car suspension building the type energy housing first. So in 2016 and in 2008, United States, the DOT first supported the first proposal, solicitation 2008, first proposal 2009 on the ocean energy side. 2013, the set of Water Power Technology Office. 2019, the finite powering for economy. Okay. So after that, I worked 2 years on such kind of energy housing from car, from building. I said, okay, look like there are a lot of similarity. The vibration frequency almost same, and the amplitude, similar structure, and the wave is almost same. I tend my research to the ocean wave side. Through the senior design, we build a motion rectifier. Later, we get better funding to work on all kind of wave energy converter. And then we also work on so-called blue economy. In that time, there's no such kind of word yet. So basically the idea is the harvest energy we use for the in-ocean localized application. So this is my work on the Willful Energy side. And I quickly show 2 project results to you, and this is the video. So this boy move up and down, you can see the energy housing, right? So, and what's inside? This is move up and down the draw one generator. This is, I show you this video, please pay attention to the generator. I need to use this one. So this is generator, okay. You say generator rotate one direction, and this move up and down. This motion rectifier, another version, okay. That one, the efficiency is pretty high. We get more than 80% efficiency. The design is still the same principle, but it's different configuration. Okay, so we tested that in the wave tank, and so we have different design. We consider hydrodynamic side. So we also did such kind of scale up 10 kilowatts prototype. We consider the structural dynamics, wave structure interaction, and the mechanical design. We also design power electronics for the grid connection. We tested in the ocean. Okay, so this is the key innovation part, motion rectifier. and this figure is say it's almost the same, right? So the only difference you say, oh, you have another turbine here, right? The difference. Another difference you say this red color we go third one we clutch. So in this design, the wheel can drive the system and the turbine can drive the system at the same time. The wheel and tidal will not fight each other. This is the result. So this wheel drive the same generator and turbine drive the same generator. We can get more power. So this is the result we show you. Okay. And I mentioned to you that we have mechanical rectifier. Just problem. Problem is like when you drive the ride the bike, flat road is not a problem. Up here is not a problem. Down here, what happens? Your bike lost control, right? You don't have brakes. Right? It will be too dangerous. Same here. We use one-way clutch, and the one-way clutch, the wheel can drive the generator, but generator cannot drive the wheel. Similar as your pedal cannot drive the bike. So in electrical domain, people did is they replace this passive diode and with active transistor. That is the synchronized rectifier. With synchronized rectifier, the current can go two directions. Not only from the input side to output side. Now the energy stored in the capacitor can draw back. So in mechanical domain, we also create such kind of system. And I didn't show you this video. Okay, we have a prototype here. In this prototype, this active motion rectifier. Basically, your generator always rotates one direction. But you can use this generator can control the input side into two direction motion. So this is another project we are working on, and Dr. Hedgie and his students is PI, and PI with a company work together. And this wheel surge device, instead of moving up and down, this row integration. So the uniqueness, we have active motion rectifier so that we can implement active control. This is in collaboration with the National Lab Tool. And I will show you a video. So that is what we tested in the tank at the Stevens. And we have two flaps, left side and right side. The two flaps were more out of phase. So the flap more out of phase. Since the motor more out of phase was the result, and the force were cancelled in horizontal direction, and this force were cancelled. Otherwise, the platform were more. And we also did an experiment with one flap only. With one flap, you can say this flap don't rotate. They just move together left and right side. Okay, this is 100 kilowatts wave energy converter with active motion rectifier. And in my view, and we click to quick. Ocean wave research is very, very challenging. There's no research convergence yet, right? Generally speaking, more energy, we want to work on wave and current energy, offshore wind, right? So we can use that to power marine transportation, power water desalination to produce hydrogen or power fish farm, right? Also can power our water desalination, produce fresh water. So the knowledge we need not only civil, mechanical, ocean, and we also electric and environment, social science, and business. Okay. So I want to draw the conclusion with my vision. Okay. So overall, I talk about energy harvesting from vehicle, from infrastructure, from sustainable ocean to enable sustainable and intelligent transportation. Actually, there are three research directions we talk about. One research direction like smart tire, the type of thing, And on-road energy harvester, we have the small energy. We use it for the intelligent transportation system, like Internet of Things, right? And second thing is 100 watts energy, like this suspension system, and at all bridge or building, and we have the energy to implement vibration control. A third thing, like ocean type of energy harvesting, it involves different disciplinary. We want to make a breakthrough and to make contribution to global energy solution. Okay, so just one figure I want to stop here, just show you. This is our figure. Okay, the red proposal didn't get funded yet. So just imagine that we talk about people now, we have intelligent vehicle, right? Intelligent vehicle, connected transportation, whatever, right? We need intelligent infrastructure too, so that we now all the infrastructure like that is designed for human being. Now you use the camera to do some analysis and to detect that. Why not use energy harvester to power roadside infrastructure? And you can use wind energy, you can solar energy, you can have vibration, right? You charge this battery, right? You have energy. You can power the wireless communication and send the data to the car, right? The car itself don't need to use camera to look into pictures. They directly tell you, okay, turn left, turn right, right? So this is the self-powered active infrastructure. Okay, I stop here. Question? Okay, thank you. Yes, please.
Thank you, Professor, for this nice presentation. So I have a generic question about energy harvesting, like can be materialized in the speed bump case. So we have discontinuous generation of let's say electricity, and we have continuous demand, which is the speed the light bulbs. So in this case, is it feasible to use batteries to
you need energy storage. So therefore, you need electronics to charge the battery, and it's fine. And the reason is for this one, when you need continuous power, the power is very, very small, right? Like you have wireless sensor, most of the wireless sensor is milliwatts level energy, right? I mentioned speed bump, you can get 1,000 watts. So you charge the energy within a very short period of time, and you can use that for longer period of time. Sure, this longer period of time, your wireless sensor will not be active all the time. Probably you every like 1 minute you wake up for 5 seconds, right? In duty cycle. Yes, it's doable. We need us to consider the energy balance. Also, we need like this one. We put wind and solar together because you have raining day, there's no solar, right? But mostly you have wind. This combination.
but battery is energetically costly. Yeah, there is loss of efficiency when storing it.
Yeah, you have the battery. There's a self-discharge, right? Depending on different type of battery, and there are some battery with very slow discharge. People use in nuclear system, it can last 50 years, and mostly battery will last months is not a problem. Yeah. Yes, please.
So, thank you, Professor, for your presentation. I have a follow-up question of Bartek, that can a supercapacitor replace a battery?
No.
And if yes, can it supply sufficient power in a piezo energy harvester?
Yeah, my short answer is no. And this is exactly what he asked. Self-discharge, supercapacitor self-discharge too quick. Right, you can not put here for weeks, right? Yeah, the best is a combination of supercapacitor and battery. Battery, you need to consider two things: how much energy is stored. Another is how much power it can provide. For example, many battery you cannot discharge that quick. So, sometimes for the sensing, it doesn't need much energy, but for the communication, it need more energy, but very short period of time. In that way, you have combination of battery and supercapacitor. You charge the supercapacitor first. Then when you need, you discharge them quick, then to power the wireless communication. This principle is exactly the same as your camera. Right? Your camera, and when you push the button, you for where you charge the capacitor, right? When you take camera, then you push down, you have flashlight. Flashlight, a lot of energy instantly is not the power, but come from the capacitor. Because now digital technology developed too quick, no one uses traditional camera. You may forgot about when you take a picture, you need to push this button and charge, and the light turn off, then you can put it down. Yeah.
So Professor, once we embed a piezo energy harvester in the pavement, so the harvester itself won't require maintenance, but the battery would require. So that would require us to, do some destructive and destroy the pavement, take out the battery, and then replace it. So is there any way to replace a battery in a piezo energy harvester?
Let me say the way. I'm not sure I agree with you that battery need more maintenance than piezoelectric harvester. Since the battery has been there for so long time, the technology is more mature. Piezoelectric side, probably you will face fatigue. This type of thing happen quicker than the battery itself. Yeah. So piezoelectric on the road, there are a lot of research there, and we need to be very careful about fatigue, right? For example, when you design that, you probably have some hard stop so that you have heavy loaded truck will not crush the piezoelectric. Piezoelectric ceramic is very, very brittle, right? Piezoelectric polymer, the energy conversion efficiency is too small. Yeah.
Thank you.
We have an online question. I'm not sure.
Okay.
I will try to, let's say that.
So can you read?
Yeah, I can read it. He wrote it in the chat. So his question is, have you looked into the change in vehicle weight due to the installation of MMR instrumentation in cars? And a follow-up question, has your group done any LCA life cycle assessment for the implementation of this technique?
Okay. So the question is the vehicle load or the vehicle mass and the energy happening from suspension. And this, you just imagine that way for shock absorber, and usually the damping coefficients for small car is about 1,000 to 2,000 Newton second per meter. Okay, so then you have heavy truck, the damping can be 5 or 10 times larger. Okay, for us, that's our advantage. We can have the same energy converter, and the only thing is we change the DC-DC converter or how much electric load we achieve different damping. So it's fine, different load, and we have different power equivalent resistor. Therefore, they have equivalent, they have different damping coefficient for different load. Second question is the life cycle or reliability of this mechanical transmission. Okay, so we run several iterations. The one I show you is the rectilinear, and this type of design can be damaged. So it was damaged actually. When we put it in the car, we get a very good result. Students get excited, saying let us drive on the speed bump. So they did, then damaged. Okay. So later we come up with another design. I didn't show here. Actually, I have in the backup slides. Oh, where's the backup? Wait. So later we have improved design. We use ball screw, and it's more reliable. And so far, it didn't get damaged this page. So let me. You can say this one, and we designed this gearbox. This gearbox is all in the oil environment. This ball screw is commercial available ball screw. It's much more reliable. Yeah. I hope I answered your question about the weight of different car and also the reliability life cycle. Yeah, and we signed a license agreement with one company. The company is in the process to do some professional life cycle tests for this system. Yeah. Yes, please.
Thank you for the nice presentation. For the transportation infrastructure energy harvester, what is the gauge? How long they will keep harvesting?
Okay, and let me say that we look into that. Okay, usually transportation system, you don't need too much power, and the communication like cell phone, this is depend on what kind of wireless network you use. If you use Bluetooth, it's a very small energy, milliwatts, 50 milliwatts. If you have cell phone tower, you usually about 1 watt energy, right? So if you dissipate the energy, let us say, even if you continue to use energy in, let us say 1%, 2% cycle, because the cell phone, you don't need to translate the data all the time, right? So we did some calculation. I couldn't remember exactly if the calculation is in 1 week, there's no wind and no solar, how much energy we need. And I think the conclusion is about 2,000 watts hour. You use a battery bank. You can buy a battery bank for the cell phone, right? It's more like the battery bank is more like a 2 iPhone battery. The battery bank is enough to last to support the system for 1 week. Yeah. Thank you. Any other question?
So if not, I just wanted to say now we have like 20 minutes with Professor Zhu.
Sure.
It's gonna be like meeting students and chatting with him, something other
Yeah.
than the presentation.
I would be glad to share my experience about career development. In the morning, I met several people. I said, before I come back to university, I didn't work on energy housing at all. And I worked in a pharmaceutical company for 4 years. Now, this is my main focus on energy housing, right? I mentioned to you that the reason what I did is when I come back to university, I think energy housing is very great area to work on. In that time, 1 year in the world, probably there are only about 100 papers published. Now, 1 year around, probably there are 2,000 papers, 3,000 papers published on this topic. So when I jump into this area, I don't have background, right? I didn't work on energy housing at all, but I identify that is a good direction. So one is the vision, this is one side. Second part is where I am, right? I don't have the background. However, I have the foundation. I know vibration, I know the control, I know the design, right? So therefore, I think with this foundation, I can create a new path. What's the new path? Large scale energy housing, right? And in that time, another work on the small scale energy housing, I mentioned just vibration system. Larger scale energy housing, you need multidisciplinary knowledge. Therefore, my background enable me to create a career path I can do better than the pioneer who already work on this topic for decades.